there's a distance, and it's a certain distance in meters, ne? Between them is a distance x in meters. So if we're looking at them from above like this, as if we're looking at a map, right? Let's say we're looking at them from above like that, or maybe it's a drone, who knows? But it's something that allows us to look at these two people from above. So person A is there, and person B is over there, ne? Now, it doesn't matter whether you are looking at them from the side, like so, or you're looking at them from the top, like that, ne? What you will see is there is a space between these two people. Now, in this, we have a 1D motion, one-dimensional motion. And what the dimension means, what is the dimension? Define dimension. All right, so a dimension is a measure of spatial extent. Spatial, the word spatial comes from space, ne? So it means relating to space. Svaka, like space. Anywhere where anything can be, it's space. All right. Now, if we're looking at this scenario here, Yamatom, it's one dimension because we are measuring one aspect of space, which is in this direction. As soon as we look at the person moving, let's say the person could jump. Person A could jump, and maybe they could jump up to here. Ne? They've jumped to position AI, A prime. Right? So here they've jumped. And after they've jumped, what that means is they could probably go up and then across, and that would be their position there. But then because there's gravity, they'll often fall down and they'll come back there. Right, so maybe let's say they land somewhere there. Right, so what that would mean is that if we're looking at this scenario from this perspective, we will see a person jump up and like jump up into the page. From here, we'd see them jump up into the page and then fall back down to a position there. So from the top, we'll still see them moving in one dimension. But from the side, we will see them move in two dimensions, go up and to the side, because that would be movement in that angle. And they'll go from up to down or up to the side, and they'll land like that. So this becomes 2D motion, right? So I just put that there. So that means how we measure this, the extent where they move in space, they would have moved across and above if they jumped. But now let's say they're not doing any of that jumping stuff, they're just walking. So now what we'll be seeing is a person walk from point A to point B. Now, if we just take a measuring tape or a instrument that can measure for us this distance here, we will just get a number that x equals. And when we get that number doesn't really tell us position A relative to B. Is it to the left, to the right? Is it north? Is it south? It doesn't really tell us that. It just tells us that position A is so many units of length far from position B, or position A, B is so many units of length far from position A. That's all it tells us. So what that then comes back to is a scalar. So if we just take the measure of a distance, for an example, the measure of a distance between 2 points, we can also look at things like the mass of an object. So all of these things, they just tell us what are the measured quantities of that particular object we're interested in. Another example, if you want to think of scalar, if a car is traveling to town, let's say Unamechi takes your bus and it's traveling at 80 kilometers an hour on the road. What that means, Goring, that's how fast the vehicle is moving over the road. So in other words, it covers a certain distance X in a certain amount of time, and that gives us the distance per unit time, which is kilometers per hour. That speed just tells us how fast the truck is going. Now, if we want to think about a vector, vector will include that size, that measurement that we have, but it will also include a direction. So you measure it across two factors. The first one being the size, the second one being the direction. And why is direction? I put mass of an object here deliberately because this becomes important when you calculate the weight or the force due to gravity, which is the mass of the object times acceleration due to gravity. né? And that weight has got a direction and it's acting in the direction toward the center of the earth. So in other words, if an object is laying flat on the ground, we assume the portion on which it rests is flat because when you've zoomed in onto the surface of the earth that much, things look flat. But when you zoom out, you realize that this curvature becomes visible. So even if in physics we indicate our scenarios as flat on flat surfaces like that, it still means the weight or the mass times acceleration due to gravity acts towards the center of the earth. That's why it's called acceleration due to gravity, towards center of earth, because gravity pulls towards the center of the earth. And that would be the direction that weight acts in. Now, if we go back to the same example here, the two people, if now the distance between A and B is known, but now person A walks toward person B or runs toward them, then that person, when they get to point B, they will have covered that distance in the direction from A to B. That is a vector. But if you say between A and B is so many meters, that's just a scalar. But if you say person A moves from point A to point B, so that means the person A walks a distance of so many meters towards person B. So when we explain it like that, we give the size and the direction. And that makes it a vector. And all the problems where we're dealing with vectors, they will have, where you give the answer, you must give a size and a direction, because that gives you the vector nature of whatever quantity you are measuring. Right? So, yeah. Examples of scalar quantities include mass and electric charge. But examples of vector quantities include force, which has a value, and the direction. It's acting in this direction, right? So we can quickly do this exercise just to see if we are catching on. Let's discuss between So we've got length, we've got force, we've got direction, we've got height, we've got time, we've got speed, and we've got temperature. So we're going to tick boxes. And the boxes are as follows, ne? So we've got scalar, vector, or something else. So just put something else. Ne? And each of these quantities, or here, physical quantities here, we are going to classify them by ticking the correct box if they are either scalar, vector, or something else. Are you ready?
Yeah.
Alright, cool. So what is length?
Length is the length. It's a vector.
Length is a vector. Why do you say it's a vector? Does it have magnitude and direction? The length of your foot, does it have magnitude? Yes, it does.
Yeah.
Does it have direction?
Nope.
It does not have direction, okay?
Yeah.
Alright, so if it doesn't have direction but it only has magnitude, where do we put it?
In the scale.
As a scalar, ne? So we'll check it's a scalar. Ne? So we'll check that it's a scalar, which is great. Where's that chapter that I was on now? I don't like it when, oh, there we go, 364. 364. Ne? Then when we think about force, ne? Force is measured in Newton, and that gives us a magnitude, but then it's also given a direction. If you remember correctly, Musa and Magdalene. So if it has magnitude and direction, where do we put it in this table?
So, wait.
It's a vector, ne? And then what about the quantity or direction? Is it a scalar or a vector?
A vector.
Direction.
A direction.
Yeah, just direction a little. Something else. Ne? What about height?
Something else.
Height.
Height.
Height is like length, but we don't consider it because length is on the horizontal plane. Length is flat, mara height it's emelage. So that's so something, I get how long something is. But height means how long something is if emelage as if mutamelage kamauto. And length means how long something is as if ipatlame fats. So what is height? Is it a scalar or vector or something else? I don't agree, Musa. Because Nakiwana height is one length. That's why I don't agree.
So it's a scalar.
Yes, it's a scalar.
How?
Because you can measure height and get a magnitude or a size. What's your height? Do you know your height? Have you measured it before? Okay, do you know the height of the table that you are sitting next to or the desk that you're sitting next to?
No.
Okay, do you have a ruler next to you?
Yeah.
Okay, take the long side of the ruler. Then also ruler so that it's not lying flat, but it measures to a certain distance above the surface of the table. Take that ruler, put your finger on the one end of the ruler ka godimo, and then the bottom end is and then the ruler is below your finger and between your finger and the table. Can you see that you can measure the distance between the surface of the table and where your finger is?
Yeah.
That is a height. So when you've measured, you get a size of something, a quantity. And because you've gotten a quantity, height cannot be something else. It can be a scalar. No, what? And then what about time? Is time a vector or a scalar, or is it something else?
Something else.
Why? Or something else?
Because no, it's a scalar.
Yes. So time is a scalar. Size and direction. So I wrote these two down because every time you think about a quantity, we know whether it's got size and direction or size only. Ne? Speed is a scalar because it just tells you how fast something is going. But velocity, which or something is going this fast in which direction. So speed is therefore a scalar because it doesn't have direction. And then what about temperature?
Temperature is a scalar.
Yes. It's a scalar. But then again, I could also be wrong with this one because it could also be just a scalar. But I would like to think it's something else because direction doesn't really measure a size of something. It just tells you in which way it's going. Is it going left, right, up, down, east, north, south, west, etc. So now that we've discussed a little bit about the different types of measurable quantities, we look at vector notation. So when we are writing, a vector usually has a bar on top or an arrow. So it can be a force, it can be velocity, etc. Right? So this is how we represent vectors. And if we just write V, F, then we are just writing the scalar quantities or the scalar versions of the force, which is just the size of the force. And then another important thing with vectors is that We can also represent them graphically. So how we represent them graphically, the quantity will have a starting point or tail, and it would end somewhere. So the ending point is called a head. Like in science, we've got draw these vectors using head to tail method. You remember that? That thing, our Shumisha head to tail method, we're going to explain it now. So when we look at the vector graphically, and we can use this method on things like a graphing paper so that we can draw these things to scale, right? So this here, this Lelo side is a measure of the magnitude or size. Ne? It's a measure of the magnitude or the size. And then let's just assume we have an imaginary axis where the thing starts, where the vector starts, then there will be a direction. Actually, in physics, we count the other way around. We count clockwise from the y-axis and go around. So this would be the angle. And that angle would be the direction. Okay? So the head has an arrow and the tail is a point or just where a line ends without arrow. So it's without an arrow. Without an arrowhead. So the other thing, there's more than one way of writing a vector, and the most important thing is that it must always have magnitude and direction. Okay. Then there are things that we use for directions, right? Yes, that's what I want. So directions, we have the following types of directions. We've got relative directions. We've got compass directions. And we've got bearings. Ne? Have you ever used a compass? Have any of you ever used a compass? Eh? Salula Shumisha compass before? Yeah? Magdalene, where were you using a compass when you used it? Geography. Okay. Musa, when have you used the compass before?
Yeah, but then it was in grade 7.
In grade 7. Okay, that's interesting. It seems like ibele khalenya. So when you were using the compass, what were you using it for?
Draw the angle. Yeah.
Bele measure the angles.
Yeah.
Okay, angles chime. Also, Opal.
Yeah.
It's fine. I mean, grade 7 gekhala, I put geometric now, so that's like more than 5 years back. So, about 5 years back, 4 5 years back, yeah. So, gekhala nyana, ne? And I understand. I just wanted to test if you will remember. But we're gonna discuss those, etc. Ne? So, relative is like, again, in the same example, yeah, person A and person B. You can have different objects. It can be the Bolger snooker, like you'll see in many examples in metric for physics. A ball would move from one side to another. So in that test, in that scenario, ne, we will say if we have two balls, two objects, one object A, one object B, and object A is moving in the direction of object B, then what that tells us, Kore, A is moving in the direction towards B. Yeah, one. So this is relative direction. So relative to B. So if remember B, A guy, that's relativity. We can also look at the definition just so we can understand it better. Relative. Considered in comparison or relation to something else. An animal with a large brain relative to body size, that's a human being, or the relative quiet of the suburbs. So suburbs are quiet compared to like location. Locationing everywhere you go. Next door get tavern, the other house there's maybe people arguing or having a party. But the suburb, you don't get any of that. It's usually quiet. So relative to the township, suburbs are quiet, and relative to the suburbs, townships are noisy. That would be a relatable example. But in this case, it just means relative to B, where is A going? And in this case, B, A according to the arrowhead. Relative to the bulb at B, which direction is A moving in? Is moving toward?
To the right.
Is moving to the right. That's absolutely correct, Nemos. That's absolutely correct. And it's just as correct as saying A is moving toward B. Right, Grisha? Alright, so relative, Musa is 100% correct. A would be moving to the right or towards B. Either way, it's correct. Another way, let's say you are driving or you're in a major taxi, you're going to Mokopane or Johannesburg, then there's a direction component. Mokopane is south of Polokwane. So if you travel, let's say, so many degrees southwest or southeast of Polokwane, or let's say southwest, yeah, because you kind of travel as if you're going westward, but also to the south when you're traveling anywhere on the N1 south in South Africa. So it kind of moves towards the direction of Cape Town, which is a southwestern direction. So these ones are relative to the compass directions of north, south, east, and west. And we use this also to define directions, travel, wind speed, etc. So if a vector does not point directly in one compass direction, we'll use an angle. For example, if we have a vector pointing at 40 degrees north of west, we start with the vector pointing along the west direction, and then we rotate the vector towards the north until there is a 40-degree angle between the vector and the west direction. So the direction can be described as west, it's 40 degrees before you get north, or north, which is 50 degrees before you get west. That's the direction of that thing, of that vector. So in other words, if let's say umoki Polokwane and you're traveling to, let's say, Joburg, right? And that is north and that is south. Then there is a certain direction and angle there. And let's say that is 15 degrees, right? Let's say that measures 15 degrees. So it would be, when you're at Polokwane traveling to Joburg, you would travel south and then 15 degrees. You travel south and then 15 degrees west. Yeah, so it'd be south, 15 degrees west. Or it would be west, 35 degrees south. Either or is fine. Then lastly, we have a bearing. And a bearing starts from north. So it's relative. So bearing is relative to a fixed direction. Relative to fixed direction. And that direction is usually north, right? So if you're traveling using bearings, then if we have an angle that you're traveling on your bearing, then that bearing is relative to this direction. So we count from north and then we go clockwise and around for 360 degrees. So that would mean if you have an angle of 110 degrees, then you would have to have, for your vector, then you would have to have traveled on that bearing, and this angle would be 110 degrees. And this would be the vector. All right, so now we're gonna do the same exercise that we started with, ne? Okay, and we must classify the following quantities as scalars or vectors. So we've got 1A, B, C, D, and E. BA. Okay, so we've got 12 kilometers. We've got 1 meter south. We've got 2 meters per second at 45 degrees. We've got north 75 degrees, 2 centimeters at 75 degrees. And we've got 100 kilometers per hour at 0 degrees. Okay, so we can do that other table again. Vector or something else. Vector, scalar, or something else. Let's do that exercise again. So scalar, vector, something else. Again, scalar, size only, and vector, size and direction. Ne? Again, so. And then we're going to do the same exercise. So starting with 12 kilometers, is it a vector or a scalar?
It's scalar.
It's a scalar, ne? Why?
Because it has size only.
It only has size only, okay? Alright. And then yabobedi B.
Vector.
It's a vector. Why? Why is it a vector?
Because it has a size and a direction.
100%. It has a size and a direction, not just direction. I got Magdalene. Yes, you say everything in full. And then number C, 2 meters per second at 45 degrees. What's that? Vector or scalar? It's what? It's a vector. Why you guess?
Huh?
Why are you guessing? Because I was sure I would guess. So what is it? Is it a vector or scalar, number C?
It's a vector.
It's a vector, ne? Why?
Because it has direction.
It has a direction and
And a size.
a magnitude, yes, and a size. Number D, 75 degrees, and then there's 2 centimeters. Is it a vector, a scalar, or something else?
25. A vector.
It's a vector. Why?
Because it has direction and size.
Yes. Which one is the direction?
Direction is 75 degrees.
Yes.
Is
And
it
which one?
0?
Yeah, it's just 0.75. You can still write it like this and it will still be the same thing.
Okay.
Yeah. Then Yamafelelo, 100 kilometers per hour at 0 degrees. Leona vector. Why?
Because it has a size and a direction.
It has size and direction, 100%. You can change to the next slide now, baby. And then number 2, we've got A, which is an arrow pointing like in that direction. And then we've got B, which is there's a vector, and then it's at 60 degrees to the horizontal. And then we also have C, which is at 40 degrees which is at 40 degrees to the vertical. So we must use 2 different notations. We must use 2 different notations for each of these. So we've got notation 1 there and notation 2. Ne? So for number A, which notation would you like to use? These are all vectors, ne? So we're told that all of these are vectors. So we know that they have a size. We don't really know the size, but we can assume the size is the length of the arrow. So we can assume sizes are lengths of arrows, so that we don't have to worry about how big these sizes are. But we know that these are vectors. All of 3 of the black solid lines are vectors. So if we use notation Yamatomo to express the first vector, how would you think about it? How would you go about answering that question? You have a vector, it's pointing vertically in that direction. It's pointing in that direction. A vector is pointing this way. How would you use the notation that we know about vectors between the relative, the compass, and the bearing? Do you think we can use relative directions here? Let's start there.
No. For the first one.
For all 3 of them, can we use relative direction?
No.
Not really, ne? Like it won't be easy to use it, so to speak. So we can leave that one out and focus on the other 2, compass direction and bearing, isn't it? I get.
Yeah.
Yeah, we can ignore the relative direction and focus on compass and bearing. All right. If we write the first vector using compass notation, how would we write it?
It's moving to the north.
So we can say it's the vector and it's acting in the direction north. Yes. And what about notation 2? If we use bearing, how do we use it? Remember, bearing has numbers in it. So if we are looking at, in physics, we said we start from the north axis and we go clockwise to 360 degrees. So if something is on north, which direction in terms of angles that have numbers is it in? Is it 5? Is it 30 degrees? Is it 10 degrees? Which one is it? If this is north, what's the angle measurement of north?
You said it's 110.
I did not say it's 110. In the previous example, which is here, in this example here, this 110 is for this specific example. Or if we are looking at north, which is at 0 degrees, and we go 110 degrees that way, we go 110 degrees that way. We put our protractor here and our 0 degrees is there. And then we count 110, then we will land here. Then that's the bearing of this vector here. That's what I said. Not that the direction of north is 110 degrees. No, that's not true. So in this case, what's the bearing of this vector A?
0 degrees.
It's 0 degrees, right? So it would be the vector at 0 degrees. Can you see now how we use one of two notations for vectors that have directions like this next to them.
Yeah.
Yeah. Then vector number 2. Remember, north, south, east, west are like this, ne? Ne?
It's from north to east.
So this one would be
North to east.
it will be from north to east, right? Let's quickly review the theory so that we're sure. Okay, so the instruction is we start with the vector pointing along the direction. So this one, we start with the vector. Starting along the east axis, ne? So if the vector is starting along the east axis, then we will say east 60 degrees north. So you can say it's the vector and then it's east 60 degrees north or north 40 degrees east. Either or. And then what's the second way that we can express the same vector if we are looking at a bearing? It's actually 30 degrees, not 40. And this one, if it says 35 here, 90, that would be 75. Yeah, 75, not 35. Yeah. All right, so if we're using a bearing, we'll look at north. And between north and the vector, there's a bearing of 30 degrees. So it'll be just 30 degrees. Bearing, we always start from north, ne? Yeah, and then the last one, we started at south, and then we go 40 degrees west, or we can say west, 50 degrees south, which would be that direction. And here we can also say it's 180 plus 40 is 220. So the bearing is 220 degrees from north. Yes, it's 50. Right. Then comes another important part of drawing vectors, ne? Vectors, we have to draw them to scale. That's why there would be a graphing paper in the exam. So if something is given as 20 Newton and the one side of your page is only 210 millimeters, then you have to use a smaller scale, like maybe half the distance on the ruler is the actual distance in a concept. Maybe a scale like 1:2, 1:20, or even 1:50, 1:5. It doesn't really matter. But either or, you would use a scale. Ne? Now this scale helps us translate in geography. Musa, did you do geography ko skolo?
Nope.
Asangwa dia geography. Kwena dine geography ne? Oh, I did. Okay. Yeah. So in geography, you'd be given a map, and then they'll tell you the map is 1:50,000. So that means 1 unit on the map when you measure on the ruler if you measure in millimeter, then in real life, it's 50,000 millimeters. So 50 meters. So 1 millimeter on the page that you measure is 50 meters on actual land. So I can remember it's like a smaller, like it's like you shrink down the space that you're on or looking at. You shrink it so that you can be able to see it or fit it on a page that's convenient to carry around. Because you guys Google fast warrior. Fastly as map, and then I'll refer to it when I go to Circle Cent. It's gonna be impractical. But your phone can scale down the directions between where you are to Circle Cent. And to do that, they use a scale. Now that scale says, when I measure on my screen here, whatever I measure on my screen here, let's say I'm measuring something on a map. There's a road, and maybe there's a yard there, and give me it's more. If I'm measuring something there, right? Right, if I take this ruler and I measure something on this map here, and the scale tells me it's 1:50,000, what that tells me is that when I'm measuring here and I measure 1 millimeter, then on actual land, 1 millimeter on map is 50,000 millimeters on actual land, or 50 meters, So that means if kitchen distance out to and that distance illegally distance here 1 millimeter, then here, if I put myself like that person on Google Maps, if I put myself there, then I'll be looking at 50 meters. So literally, like 50 meters, maybe half a soccer pitch? Let's see, dimensions of a soccer pitch. How long is 50 meters? Google. Compared to everyday things. 14 common comparisons. I think Musa, we should share screen with you so you can see what's going on. I realized I haven't shared screen. So yeah. So we're gonna look at 14 common comparisons of 50 meters, right? How long is 50 meters? Half a soccer pitch, so I was right. So maybe that person is a bit out of scale, they're too large. But if the map is that big, then when I measure, then it means I'll measure 1 millimeter, and that millimeter on the map represent this distance on the actual thing that's measured on the map. It represents the distance from there to there. You can also think of 50 meters as an Olympic-sized pool from long end to long end, half a 100-meter dash, 2 tennis courts back to back, bowling lanes. Have you been bowling before? Any one of you, have you ever been bowling? Never. Musa, Salwa Dala bowling. This game. As long as I Salwa Wana Mar TV or in movies or whatever. You've seen it, right? Mall of the North Salwa Wana. Le Savannah.
Yeah.
Yes.
Oh, yeah.
2.5 cricket pitches. So more the way they bowl for cricket, if you put them back to back, so Tomamo, and then Walayong or Tomamo Yakua, and then Walayong or Tomamo Yaku. That distance is going to be 50 meters. Basketball hoop, J50. Dinamelane, that's 50 meters. J16, sorry, not 50. J16, yeah. 12 compact SUVs. So if we the Mazda CX-3 or the Honda RHV or the Jeep Renegade, J12, or if we are back to back, that's 50 meters. Or if we the Koloi, Chaosana Lieki, or if we are back to back, 9 parallel car parking spaces. So mole mo dikoloi di parkang ka thoko tsa pat molo khwetsa ho eso. So dilo tse 9. So the parallel parking tse 9 e ga di latelang di go fa 50 meters. 66 human footsteps. Okay, that's a bit of a stretch. But if you take the average step length to be 0.6 meters, let's see if that checks out mathematically. So we're gonna take 50 meters and divide it by, well, I get 83. And that's because my step length is 0.6. That's why. So I'd have to walk 83 times to get 50 meters. 25 standard front doors. So I'll be mamati. Kabotelele like lebati la mathomo. Then on amechalele nka godimo. And so on. Then you get 50 meters. Yo, last number ya mattress. 25 queen size mattresses back to back, and Statue of Liberty without the pedestal. So in other words, from where the statue starts to where it ends, that's 50 meters. So that at least are for now how we can visualize 50 meters. So we use scales like that so that if you try to measure all those things and fit them into your page, but it's not like that. So imagine you're given a 50 Newton large vector and you have to represent it on a, so your vector is 50 Newton and you want to represent it on the page in your exam pad. You want to represent it on the page in your exam pad, but it's too large to fit in your exam pad or your notebook. So what do? You scale it down. So Tanori, if I measure 1 centimeter on my ruler, elegantly maybe 5 Newton. Then it means 1 centimeter already 5. That will elegantly 50 Newton. So you would say 1 centimeter equals 10 Newton, then 50 Newton, it's all gonna lay 5 centimeters. So then on your ruler, 5 centimeters, then you can quickly write that down and even draw that capilla on your, as your answer, right? So you decide upon the scale and then you write the scale down. Then you decide upon a reference direction. So reference direction, do I start from north, which is 0 degrees, etc. And then because on a scale, you can determine the length of the arrow by drawing it. And then at the end of the vector, you put an arrow, but tomang maybe tomamole. And then you will then write the vector as kaufelele. So if we have to draw a vector, for example, you can switch to draw vector. So let's say our vector is 6 meters per second north. That's a velocity vector, right? Then we can say 1 centimeter is 2 meters per second. That means if we have a ruler, one, two, three, four, 5, 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So now I'll have 1, 2, 3, 4. 5, right? So it's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Yes. Okay, cool. So this is our ruler. And our vector is 6 meters per second north. And this is 0, 1, 2, 3, 4, 5, and 6. Ne? So we and then we put it on a piece of paper, and then we start to draw. So we know that this distance here is 2 meters per second. So 6 meters per second, you felt like for our vector on the ruler, where's 6 meters per second going to end? You felt like if that is 0 there, and this distance here is 2 meters per second, then 6 meters per second, how long is it going to be on our ruler? If that's 2 meters per second, how do we get to 6 meters per second?
On 3.
On 3 again. So it's 2, 4, 6. So then our velocity vector is going to be it's going to start, let me erase this. It's no use complaining about how cold it is, eh? So your class is gonna finish, so we're gonna finish. So our vector is gonna start there, and it'll end at 0 centimeters. So now we've got our 6 meters per second, and what's our direction? North. So we can just leave it at that. Do I want? Then our second example, the following vector is a displacement, and it is 16 meters east. Ne? What does that mean? Or the scale rather is 1 centimeter is 4 meters. So again, we've got a ruler. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 1 centimeter, 2, 3, 4, 5, 6, 7. All right, and then Scale sarna we've got 1 centimeter. Elegantly 4 meters. In order for us to get to 16 meters, but starting here, how far must we count in the direction of east? If we have a scale of 1 centimeter to 4 meters, how far on a ruler must we count to get to 16 meters? If that's 4 meters, how much do we count? How many times do we count on the ruler until we get to 16? Mental or ring? Mental or fourth amarang? Hmm?
16.
How do we get the scale right? How do we get the measurement right to get to 16 meters so that represented that vector? I agree we did it for this one here. Yeah, velocity.
Yeah.
A. So we do the same type of action. It's the same type of action. We start at 0. We have to count 16 meters using the scale where 1 centimeter is 4 meters. So how many centimeters must we count to get to 16 meters?
Should be 4.
Should be at 4, ne? So move all the way to 4. So that would be 16 meters east. And that's the distance here, 4 centimeters, because 4 centimeters times 4 meters would be 16. So that's how we draw our vectors. All right, then another thing that's important, Gadi, vector. So properties of vectors. Equality. And this means if kinale a vector that has a certain magnitude and direction, and there is another vector somewhere in space, maybe let's say it's there, and the magnitude of vector A, the magnitude of vector A equals the magnitude of vector B. Ne? So if I take the size of vector A and the size of vector B, and they both have the same direction, then what that means, these vectors are the same. Ne? Magnitudes are the same. So same size and same direction, then it's the same vector. That's property number 1. Property number 2 is, okay. If we have a vector that has an opposite direction to the reference positive direction, we say it's a negative vector. So for example, let's say we are throwing a ball up in the air, right? Person is throwing a ball up in the air. If we assume that down is positive, then the ball being thrown up, that's in the negative direction. And if we assume to the right as positive, in the case of two objects moving, then if, let's say object A and B, then if object B is moving to the left, then it's a negative vector. All right, so that's negativity. So negativity simply means if a vector moves opposite to the initial or reference direction that was chosen. Ne? Secondly, then another thing that's important is the addition and subtraction of vectors. So when vectors are added, we take into account their magnitudes or their sizes and direction. So if two people are pushing a heavy box, one is standing behind it and pushing it. So vector addition. Yeah. So one person is pushing. One person is pushing and the other one is pulling it. Ne? Ne? So this one is pulling with F2 and this one is pushing with F1. Ne? Then the total force applied on the block would be F1 plus F2. And of course, we take into account the direction. Because they are both moving in this direction. So then it's likely that the total force would be positive. So it's also, we can also understand the concept of vector addition by understanding the displacement vector. And displacement is simply the vector which describes a object's position. So it's a vector that points the initial position to the final position. So let's say this box moves from there and it's somewhere there after the whole pushing and pulling. Then that displacement, this displacement, which is a vector, shows us that before box was here, but now after box is here. So when after the box is at a different location, it's been displaced. We can quickly look at what it means to displace something. Salela kwa ditabeng ba bolela ka displaced refugees or something like that. I'll tell you ditaba ba bolela ka batho ba tswa other countries, ba chabela countries tse ding because more higher overs. And then they use the word displacement. Actually, so that is because whatever is happening in that area is causing a discomfort for people to stay there. And because it's not comfortable to stay there, people get displaced. So in other words, they move from one place to another. It's the act of being displaced. Right? Displaced, the word place, so displace, to displace would mean to change the location of something. So in other words, it would be a situation in which people are forced to leave the place where they were normally living. That's one way of thinking about it. And that process of moving something from where it usually was or where it was when we first observed it to a different place, that is displacement. And yeah. Likewise, when we subtract vectors, vector subtraction, if let's say we have that same block, but for some reason the friends who were supposed to push it and pull it in the same direction, they're angry at each other, or we don't know why exactly, but for some reason the person on this side will start pulling it and the person on the other side will also start pulling it. Ne? So now this one is pulling this side, and this one is also pulling that side. Ne? Then F total should be, so if we take this direction as positive to the right, ne? Then F total would be F1 plus negative F2. Why we put negative? Because it's acting in the opposite direction as we are told by the illustration, or by the fact that, or by the problem statement. That being said, the total force would be the force that person A exerts minus the force that person B exerts. And that would be the vector subtraction. So in other words, if F1 is 5 Newton and F2 is 2 Newton, so in other words, person 1 is pulling with a larger force than person 2, then F total would equal F1 minus F2, which is, or we can even start there with the plus negative F2, which when we substitute the 5 Newton, it would be 5 plus negative 2, which is 5 minus 2, which is 3 Newton. But because it's positive, then it's to the right, because it's positive. And then lastly, we have a resultant vector. So hopefully these last two examples, we were working out the force total, ne? The total force. This part here that we just did here actually shows us this concept that we're talking about, yeah, the resultant vector. Resultant vector, ne? So resultant is it's a result of the addition or subtraction of vectors. So in other words, at the end of the pulling and pushing, what's the result? So let's look at block number 1, which is being pushed and pulled in the same direction, right? F2, F1, and scenario 2, where the same block, or maybe not the same block because this one looks slightly longer. But we've got a block. Let's say it's the same block this time because they look like they're the same size. And this time, this one is being pulled that way. This one is being pulled the other way, right? So we'll just say F1, F2. And for some reason, F2 is given as 20 Newton and F1 is 15 Newton. And both are to the right and positive. And to the right, we regard as positive. So that means, in this case, the resulting force or resultant force would be F1 plus F2. And in this case, the resultant force would be F1 plus negative F2, according to our convention, which tells us that to the right is positive. That means to the left is not positive, so it's negative. And what this means is when we substitute, F1 is 15 Newton and F2 is 20 Newton, and the sum is 35 Newton to the right. But in this case, when we substitute, we will have 15 Newton plus negative 20 Newton. The end result is 20 negative 20 plus 15, and that gives us negative 5 Newton, which is 5 Newton to the left. That simply means that this block is effectively moving towards the left. And the illustration would be like, simply put, if we think about this, this would be, the resulting force would be 5 Newton in that direction. And for this one, the resulting force would be 35 Newton in that direction. Then lastly, we've got what we call an equilibriant. Equilibriant, the word equi means equal. So with an equilibriant, it's a special vector that has the same magnitude as the resultant vector, but in opposite direction. So equilibriant equals resultant in size, but acts in opposite direction to resultant. Ne? So what this means is, in the first example where we have a block that has a resultant force of 35 Newton, then the equilibriant, F equi, would be 35 Newton in that direction. And likewise, if we have that force, which is resultant force, that equals 5 Newton, then the equilibriant would be 5 Newton in the opposite direction. So in other words, the equilibriant force equals negative the resultant force. Ne? So we can end here for vectors. Does it clarify some things that might also appear in your matric work, Musa?
It does.
It does. Ne? So it's always important we start where the concept starts, because these concepts, they build onto each other. Yeah. So the same concept of vector as we have it here in grade 10, we'll have it in grade 11, in matric, and in university. You still think about it in the same way. So I just happen to be able to explain them to you because I studied engineering